Good morning, everyone. My name is G. Vishnumurthy, lecturer in physics, Government Degree College for Women, Vanaparthi. Today, my topic is thermodynamics. In this section, the objective is discuss energy conservation principle and model of energy transfer, describe the boundary work of various thermodynamic process, define the first law of thermodynamics, cyclic process and process enthalpy, mechanical equivalent of heat, that's Joule constant, specific heat, internal energy, and enthalpy. Today I covered these topics. The thermodynamics is taken from thermal plus dynamics. Thermal plus dynamics. Thermal means heat, dynamics means power. That means thermodynamics is equals to heat power. Heat, kind of energy transfer, a temperature difference is known as heat. The power capable to work. If you done a work, we will have some power. Thermodynamics, it is a science of energy and energy transfer. Here the conservation of mass principle is there. Here you see this mass input and mass output. Here in this section, the system uses the conservation of mass equation. And here you see this, the water is flowing from this area and the water is coming out from this area, but the system is stable. The conservation of mass principle states the following: net mass transferred to or from a system during a process is equal to the net changes in the total mass of the system during the process. Entire the process, the net amount of mass will be stable. Here you see this, m input minus m output is equals to delta m of system, where delta m is the system taking the energy from input. The total mass transfer is equals to m input minus m output, and the net change in mass is equals to delta m in the rate of form as defined as m input minus m output is equals to dm, that is the mass taken for the system by the variation in time, that is the rate of change in mass is always equal in a system. M input is equals to total mass enter into the system, M out is equals to total mass leaves from the system, and dm system is equals to net change of mass within the system. The mass within the system is used for the some work, and here are some applications areas of thermodynamics. Here you see this, the human bodies, air conditioning systems, aeroplanes, car radiators, power plants, refrigeration systems, so also are example for the thermodynamics. And now here you see this, the types of heat transfer and work transfer. Now heat transfer to the three cases, that is the heat transfer from one body to another body or one system to another system. In the process of three processes are there. One is convection, second one is radiation, and third one is conduction. Here you see this the radiation process is entirely different from the conduction to convection, because of here in this radiation process the two systems do not physical contact to each other, but here in the case of convection and conduction the two bodies are compulsory physical contact. And the mode of heat transfer, from how the heat transfer to the system by means of the work. The work is divided into again electrical work and the mechanical work. The mechanical works are so many types, that is the boundary work and the gravitational work spring work, and shaft work. So some form of work are there. So this is the structure of heat transfer. So mainly the heat is transferred from one body to another body by means of three processes: convection, conduction, radiation. In radiation process there is no thermal contact with each other, but in the case of convection and conduction the body is compulsory thermal contact with each other. So, and the basic concept of thermodynamics, here you see this: the hot coffee at 70 degrees centigrade and the cool environment is 20 degrees centigrade. That's why the heat is transferred from coffee to cool environment, because of the property of heat always flowing from hot body to cool body, or whether the heat is always transferred from uh, hot system to cool system. So since which deals with the energy transfer, and it's a coffee on physical properties of a substance. And the microscopic or classical approaches of the thermodynamics is, it is not concerned with the behavior of individual molecules. This effect can be perceived by human sense or measured by instrument. Examples: pressure, temperature, volume, so on. So these are the microscopic properties. Macroscopic, those are macroscopic. And the microscopic or statistical approaches of thermodynamics are based on the averages behavior of large groups of individual particles. The effect of molecular motion is considered for the example for the microscopic properties of thermodynamics. And the system and the control volumes are there. The here you see the environment, total environment of thermodynamics is like this. uh, the total this is called as the pink color is called as the system, and the dark line which is called as the boundary, and out of the boundary is always called as the surroundings. Okay, the system, boundary, and surroundings. A system is defined as a quantity of a matter or a region in space chosen for study. Surroundings, the mass or region outside the system boundary is called as the surrounding. And let we go to boundary. The real or the imaginary surface that separates the system from its surroundings is called as the boundary. Okay, the surface which is dividing the surroundings to system is known as the boundary. It is a imagine what. So the boundary of a system can be fixed or movable, because of sometimes we will move the boundary surface, sometimes the boundary surface will be fixed. System may be considered to be closed or open. Sometimes the system is closed. Example, the n-butane is filled with a cylinder of 14 kgs. Is known the entire gas is called as the system. It is closed within the cylinder, and the cylinder is known as the surface, and the outsides are called as the surroundings. So the system may be considered to be a closed or open. And the thermodynamic system and types. How the thermodynamics can be divided into a specific region in which the transfer of mass oblique energy takes place is called as a system. To a thermodynamic system, two things may be added or removed. Those are called as the energy, like heat and work, and second one is matter, that is always preferred as mass. Classification of thermodynamic system is closed or non-flow, open or flow, isolated, homogeneous, and heterogeneous. And these are the classification of thermodynamic systems. The closed system, the example for the closed system is called as the n-butane is filled within the cylinder is known as the closed closed thermodynamic system. The open the flow, open or flow, when we open the regulator of the cylinder, and then the n-butane is transferred from cylinder to gas. So that is called, when the regulator is open, then the system is called as the open or flow thermodynamic system. Isolated system, an isolated system is, it is not interacting with the surroundings, then it is called as the isolated system. Homogeneous system, In the homogeneous system, the properties of the particles are same, then the system is known as homogeneous system. And the heterogeneous system, when we add sugar or salt into the oil, then the two formations are there within the system, so that system is called as the heterogeneous system. Here you see that the closed system is like this. This is the closed system. The no mass can cross system boundary, and the energy may cross the system boundary, because of the when the boundary is boundary is transparent, then the energy will transfer from system to surroundings to system, but the mass do not change from the system to surface. Here you see the yellow colored is known as the boundary, and the heat or work out from the system, and the heat or work getting into the system. So this is called as the closed system. Again we will see the open system. The mass may cross the system boundary, the control surface, the energy may cross the system in boundary. Even in this open system, the mass and the energy both are transferred from system to surroundings, and surroundings to system. That's why it is called as the open system. And we will go to isolated system. No interaction between the system and the surroundings. Neither mass nor energy can cross the boundary. So in this isolated system, the energy as well as the mass do not change, do not cross from system to surroundings and surroundings to system. This is purely a theoretical system, and it is called as the theoretical. Isolated system is also called as the theoretical system. And here you see this, the differences between the open, closed and isolated system are there. This is the open system because of there is no cap on the open, and this is the closed system. The liquid is closed in the bottle, and the bottle open will be closed. And here you see isolated system is filled with, the bottle is filled with the water, and again the open is closed with the cork, and this entire system is taking in a boundary. So this boundary is dividing the surroundings to entire system. So these are the and the homogeneous and the heterogeneous systems are the differences. The homogeneous system exists in the single phase, and the heterogeneous system exists in the more than one phase. Here you see this two phase system. It is called as the heterogeneous, and it is only one phase system. It is called as the homogeneous system. Here you, in the homogeneous system, example is sugar solution. When we add sugar into the water, then the sugar is completely dissolved in the water. The pace of the sugar solution is same. So that is called as the homogeneous system. But here you see this, when we add sugar into the liquid, like palm oil or sunflower oil, the sugar do not dissolve in the liquid, that is the sunflower oil. So that's why it is the two pieces are there, that is the sugar and the oil. Or example for another liquid phase, here you adding the silica phase. For example, if you add silica into the water, silica do not dissolving in the water. That's why the silica is going to bottom surface of the glass, and the water is upper surface. So there are the two pieces are there. One is the silica phase, and another one is the water phase. So this type of system is called as the heterogeneous system. So these are the classification of the thermodynamical systems. One is isolated and open system, and closed system, heterogeneous and homogeneous systems. And the thermodynamics properties are there. The mass, these are the terminology used in the thermodynamics. Like mass is a quantity of a matter, weight, force exerted on a body by gravity, volume, space occupied by matter is called as the volume. Specific volume for unit mass is called as the specific volume. Specific weight A specific weight per unit volume is called as the specific weight, and the density mass per unit volume of a substance is called as the density. Temperature degree of hotness or coldness is called as the temperature. Pressure, the force exerted per unit area, is called as the pressure. P is equals to F by A. And specific heat, energy required to rise or low temperature of a substance about 1 Kelvin or 1 degree centigrade. 1 degree centigrade is called as the specific heat. The specific heat is taken in two conditions. When the pressure is constant, then the specific heat is known as is denoted by Cp. When the volume is constant, then the specific heat is denoted by Cv. And internal energy of a body, the energy contained within the system, is called as the internal energy of a body or a system. Work, kind of energy transfer, is called as the work. Acting of force, flow, working direction. Work W is equals to F into S. The multiplication of force with the displacement is gives the work. And heat, kind of energy transfer. Example for the temperature difference is called as the heat. Enthalpy, the total energy of the system, is called as the enthalpy, that is IE plus FW. So these are called as the thermodynamic terminology or the thermodynamic properties. Here you see again intensive or extensive properties of thermodynamics. Is if you see intensive property, the property which is independent of the mass of a system, such as intensive or extensive property. Intensive properties are like the property which is independent of mass, independent of the mass of a system, such as the temperature, pressure, and density, and the specific volume. So these properties do not depending upon the mass. That's why these are called as the intensive properties of the thermodynamics. And extensive properties, the property which depends upon the mass of a system, such as the volume. Volume V is equals to volume is depending upon the mass of a system. And internal energy, it is also depending upon the mass of the system. And enthalpy is also depending upon the mass of the system. So that the volume and internal energy and enthalpy are called as the extensive properties. And the density and specific volume and the temperature and pressure are called as the intensive properties of the thermodynamics. And the types of work, that we have already noted that there are a variety of way in which work can be done on or by a system. If you apply external work or external pressure on the system, then the work is done by the system, done on the system. If you cannot apply any external work on the system, when the system is work, then the work is done by the system. Okay, so the first one is the displacement or boundary work, that is denoted by W suffix B is equals to integral 1 to 2 PdV. Here 1 and 2 are called as the initial, 1 is called as the initial state and 2 are called as the final state. So the WB, that is the displacement work, is denoted by WB is equals to integral 1 to 2 PdV. Here the PdV is known as the work. So work which is done from state 1 to state 2. So that is the displacement work. And the second one is electrical work, that is denoted by WE is equal to integral 1 to 2 and VI d tau. We here d tau is called as the variation in torque, and VI is called as the resistance RV, and V is denoted by, and shaft work is denoted by WSH is equals to integral 1 to T capital T d theta. Here is the T is the time period and d tau d theta is the variation in theta, and it is equals to write as WSH is equals to integral 1 to T into W. So work is elastic solid rod, that is W elastic is equals to integral 1 to 2 sigma n ADX, where is the dx is
called as the variation in displacement, and A is the area. And work with the stretching, that is W surface is equals to integral 1 to 2 sigma s dA. These are the different type of works. And now we are going to density and specific gravity. Density, so density is the mass per unit volume, specific volume is volume per unit mass. So that is denoted by rho is equals to m by v. The units of the density is equals to kg per meter cube. Specific weight, the weight of a unit volume of a substance, that is gamma s is equals to rho into z. The units for the specific weight is equals to newton per meter cube. And specific volume is denoted with a small v and is equals to v by m, and that is equals to 1 by rho. That is the specific volume. There is no units for the specific volume. And specific gravity, the ratio of the density of a substance to the density of some standard substance at a specific temperature is known as the specific gravity. So it is a ratio, that's why there is no units for the specific gravity. And the specific gravity is equals to rho by rho h2o. Rho h2o means the water. H2o means the water. And the pressure, a normal force exerted by a fluid per unit area is called as the pressure. That is 1 pascal is equals to 1 newton per meter square, or 1 bar is equals to 10 to the power of 5 pascal, that is equal to 0.1 mpa. It is equals to 1000 kilo pascals. And 1 atm, 1 atm is equals to 101,325 pascals. And these are the units and values of the pressure. The normal stress or pressure on the feet on a chubby person is much greater than on the feet of a slim person. So that is the slim person have the 0.23 kg of per centimeter square, but in the case of fat man, that is 0.46 kg fit per centimeter square. So this is about pressure. And the absolute, these pressures are divided into three types. One is the absolute pressure, and the gap pressure, and vacuum pressure. The absolute pressure, the actual pressure at a given position, it is measured relative to absolute volume, that is absolute zero pressure. And gauge pressure, the difference between the absolute pressure and the local atmospheric pressure. Most pressure minus measuring devices are calibrated to read zero in the atmosphere, and so they indicate gauge pressure. And third one, vacuum pressure, the pressure below atmospheric pressure is called as the vacuum pressure. And the vacuum pressure is denoted with and next we will go to specific heat capacity. Quantity of heat required to rise the temperature of a unit mass of the material through 1 degree Celsius is known as the specific heat capacity. The specific heat at constant pressure is denoted with Cp. Specific heat at constant volume is denoted with Cv. And Cp is equals to 1.003 kilojoules per kg kelvins. And Cv is equals to 0.71 kilojoules kg kelvins per air. And we universal Ru is equals to Cp minus Cv, or Cp minus Cv is equals to Ra, where R is the Rydberg constant. And now the state pressure and cycle. State pressure and cycle, you see that state, it is a condition of a system as defined by the values of all its properties. It gives a complete description of the system. The process, any change that a system undergoes from one equilibrium state to another equilibrium state, then that is known as the process. Here you see this is the water graph, and the state 1, the material will goes to state 1 to state 2, and in between the state 1 to state 2 is called as the process path. And so this is the relation between state to process. And now we are going to state and equilibrium. A state, it is the condition of the system, namely temperature, pressure, density and composition. It's known as the state of the system. And equilibrium, in an equilibrium state there are no unbalanced potentials or driving forces within the system. If the mass, temperature, volume are the same in the liquid, then the system is known as the equilibrium state. And state and equilibrium, here are we see that thermal equilibrium and mechanical equilibrium are two types in equilibrium. And first one is thermal equilibrium. The temperature is the same throughout the entire system, then the system is in thermal equilibrium. And mechanical equilibrium, there is no change in pressure at any point of the system with time. Irrespective of the time, the pressure will be constant, then the system is known as the mechanical equilibrium state. And state and equilibrium, the phase equilibrium is also another equilibrium. A system which is having the two phases, and when the mass of each phase reaches an equilibrium level, then the equilibrium state is known as the phase equilibrium. Another one is the chemical equilibrium. The chemical composition of a system does not change with time. That is, no chemical reactions are occur, then the system is in chemical equilibrium. And the thermodynamic cycle is there. You see the system here. This is called as the system. This system is filled with some gas, and here it is called as the piston. It is called as the piston. Initially the piston takes place in this position 1. A entire figure shows the cylinder which contains the gas, and when we apply some external force on the surface of the piston, then it will goes to one state to another state. What will happen, let's see in this figure. So here in this figure, the volume of the system is denoted with V1, and the pressure at initial position is denoted with the P1. And therefore when we apply some external force to the piston, then it will goes to two position. So that's why the volume will be increases as well as the pressure will be the volume will be decreases as well as the pressure will be increases. Here you see that we will go to V1 to V2, then in x direction, in x-axis we will goes towards the 0 point. That's why it shows the decreasing of the volume. But here you see the graph, here one state to two state of pressure, the pressure will be increases in y-axis. So the path, here you see the path and cycle, the path series of states through which a system passes during process. To describe a process completely, one should specify the initial and final states. The cycle, a number of processes in sequence bring back the system to the original condition. So this is about the thermodynamic cycle. And second one is boundary work. What is the boundary work? The work associated with a moving boundary is called as the boundary work. Therefore the expansion and compression work is often called as the moving boundary work or simply boundary work. Some call it the PDV. The work is done by the system or on the system is denoted with the PDV. The moving boundary work is associated with the real engines or compressors cannot be determined exactly from a thermodynamics analysis along, because the piston usually moves in very high speeds, making it difficult for the gas inside the maintaining equilibrium. Then the state through which the system passes during the process cannot be specified, and no process path can be drawn. Work being a path function cannot be determined analytically without a knowledge of the path. Therefore, it is determined by direct measurement of real engineers or compressors. The boundary work, in this section we analyze the moving boundary work of a quasi-equilibrium process, a process during which the system remains nearly in equilibrium at all times is known as the quasi-state. A quasi-equilibrium process, are also called as the quastic process, is closely approximately by real engines, especially when the piston moves at all velocities. Under identical conditions, the work output of the engines is found to be a maximum and the work input of the compressor to be a maximum when the quasi-equilibrium processes are used in place of non-quasi-equilibrium processes. Here you see this the boundary work for various thermodynamic processes are there. The boundary work is denoted with the WB is equals to integral 1 to 2, and PdV, here the P is called as the pressure and dV is variation in the volume. Because of we are working with this system at the constant pressure, that's why there is no variations in pressure but variations in the volume. So that WB is equals to 1 to 2, PdV is equals to 0 because of the reversible constant volume or pressure in a constant volume process. The working substance in a constant pressure, that is dV is equals to 0, then we will put dV is equal to 0 in the equation, then integral 1 to 2 P into 0 is equals to 0. So in a constant volume process, the working substance is contained in the rigid vessel, hence the boundaries of the system are immovable and no work can be done on or by the system. So other the pedal wheel work input, it will be assumed that constant volume implies zero work times stated otherwise. So this is the boundary work for various thermodynamic processes. Another one is you will see the boundary work for various thermodynamic processes. Another one is the reversible constant pressure. Before we will see at constant volume, then we will see the constant pressure, that is P is equals to constant. Then here you see that PdV is equals to work and P is equal to 0, then we will substitute as 0. So therefore the reversible constant pressure, at constant pressure the WB is equals to integral 1 to 2 PdV. Here the P is constant and there is no variations in P, and but variations in volume is equals to V2 to V1. That's why the equation we got as WB is equals to P into V2 minus V1 after integrating the equation. So therefore WB is equals to, then V is converting into MV by MV, therefore MP of V2 minus V1 are the velocities. V is converting into velocities, then we got the MP of V2 minus V1. So that is, and the boundary work for various thermodynamic processes are there. Reversible temperature or isothermal process, or PV is equals to constant and T is equals to constant. So a process of a constant temperature is called an isothermal process. When a working substance in a cylinder behind a piston expands from a high pressure to low pressure, there is a tendency of the temperature to fall. In an isothermal expansion, heat must be added continuously in order to keep the temperature at the initial work. Here you see this the figure shows about the boundary work. Various thermodynamic processes are there. Now here we see the equation for the various thermodynamic processes are T is equals to constant and T1 is equals to T2. Therefore we know that the ideal gas equation PV is equals to MRT or NRT. Then it is right as PV is equals to C, and PV is equals to P1, V1 is equals to P2, VT is equals to C. Then PV is equal to C, then P is equal to C by V. C by V, we know that WB is equals to integral 1 to 2 PdV, and we will substitute P is equals to C by V in this equation. Then we got the integral 1 to 2 C by V dV. Then we achieve where C is the concentration, it will comes out from the integration. Therefore C of integral 1 to 2 dV by V is equals to C log V2 by V1. So therefore it will be written as WB is equals to P1 V1 log V2 by V1. So this work is known as the boundary work for various thermodynamic process, that is the constant temperature. And now the boundary work for various thermodynamic process, that is the reversible adiabatic process, that is PV power of gamma is equals to constant, is known as the adiabatic process. An adiabatic process means no heat is transferred to or from the fluid during the process. Such a process can be reversible or irreversible. The reversible adiabatic non-flow process will be considered in this section. So in an adiabatic expansion, the work done W by the fluid is not the expense of a reduction in the internal energy of the fluid. Similarly, in an adiabatic compression process, all the work done on the fluid goes to increase the internal energy of the fluid. So here you calculate the work done WB from PV power of gamma is equal to C. So therefore P is equals to C by V power of gamma. Then we will substitute this into the WB is equal to integral 1 to 2 PdV. Then we got the integral 1 to 2 C by V power of gamma into dV. Then WB is equals to C integral 1 to 2 V power of gamma dV. So therefore we got WB is equals to C of V power of minus gamma plus 1 by minus gamma plus 1 minus V1 power of minus gamma plus 1 by minus gamma plus 1. So this is called as the reversible adiabatic process. Here the boundary work for various thermodynamic processes are there. So that is denoted by this WB is equals to P1 V1 minus P2 V2 by gamma minus 1. Another one, WB is equals to MR of T1 minus T2 by gamma minus 1. So this represents about the temperature. By means of the temperature the work is done. This represents the pressure volume terms of work. And next we will go to thermodynamic work. The positive work is done by a system when the sole effect thermal external to the system could be reduced to the rise of a weight. So unit of a work in Newton meter or joule. Work flow into the system is negative, and work flow out of the system is denoted with the positive. Here you see this figure shows the thermodynamic work, how to will take a thermodynamic work. And next we will go to thermodynamic heat. So energy transferred without mass transfer between the system and the surroundings due to the difference. So energy transferred without mass transfer between the system and the surroundings due to the difference in temperature between the system and the surroundings. The unit of the heat is joule or kilojoule. Heat flow into the system is positive. Heat flow out of the system is negative in corresponding with the heat. So energy and forms of energy. Energy is the capacity to do the work, and form of energy is different types: stored energy and energy in transition form. And now stored energy, the internal energy that is called as the stored energy. It is the sum of kinetic energy of individuals, atoms or molecules. That kinetic energy occurred by external heat supplied to the system. It will converted to work. Some energy always stored in the system, not fully converted to work. So change in the internal energy, that is equals to mCV of T2 minus T1 kilojoules. Now enthalpy, we are going to enthalpy. Internal energy and pressure volume product is known as the enthalpy, that is denoted with the capital H. H is equals to U plus PV. And change in enthalpy is denoted with mCp of T2 minus T1 kilojoules. where m is the mass in kg and Cp is equal to specific heat at constant pressure in kilojoules per kg, and T2 minus T1 temperature difference in kelvins. And now stored energy, the kinetic energy passed by the body by virtue of its motion is known as the kinetic energy. So change in kinetic energy is equals to 1 by 2 into m of C2 minus C22 minus C11 Newton meter. So flow energy required to make the flow of the system in and out of the device. So change in flow energy is represented with P2 V2 minus P1 V1 Newton meters. And now we will go to zeroth law. If two bodies A and B are in thermal equilibrium with a third body, that is C, independently, then these two bodies A and B must be in thermal equilibrium with each other. So the application is there in TA and TB are the two variables. These are thermally equilibrium with the TC. Then we will say that T and TB are also thermally equilibrium. So this law is known as the thermodynamics of zeroth law. And from this zeroth law we have the conservation of mass principle is there. So that is here you see from the figure we will draw in the rate of forms as m input minus m output, that is the net total mass transfer is equals to dm system by dt, that is the net rate of change in mass. So that is the both are cancelled, that is m input and m output is equals to both are cancelled. Then dm system, that is the dm system by dt is equals to 0, then the m system is equals to constant. So consider the energy conservation principle, then we will draw as E input minus E output is equals to delta E system. So this is about the conservation of mass principle according to zeroth law. And the energy conservation principle, here you see that energy conservation principle also is there. E input minus E output is equals to delta E system. So here the net change transfer, net energy transfer by heat and work, and delta E system is change in the internal kinetic potential, that is the energies. For a closed system undergoing a cycle, the initial and final states are identical each other, and thus E2 minus E1 or E2 is equals to E1, then we will substitute E2 minus E1 is equal to 0, then delta E is equals to 0. So therefore delta E is equals to 0, then E input minus E output is equal to 0, then E input is equals to E output, that is Q net input is equals to W net output, or Q net output is equals to W is equals to net output, that is equal to W out minus W in. Q is equal to Q net minus this the network output, the net work output during a cycle is equal to the net heat output.